So welcome to my talk. This is my first talk at 44Con and the first time I've attended, so it's a pleasure to be here. So who am I? So as a bit of a background, I've been working in between kind of cyber, machine learning, and AI for about 8 years now. I started in the UK's Ministry of Defence, primarily doing kind of cloud hosting, so Azure and AWS, and then did a kind of security operations center there and did some kind of machine learning there. Then ended up at kind of within defense and national security research, and I've been there kind of ever since. I currently head up a very, 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 very new AI security group at the Alan Turing Institute. So those who aren't familiar with the Alan Turing Institute, it's the UK's National Research Institute for Data Science and AI. And the team's primary focus is trying to basically make some of these kind of academic research, the threat models in them, actually realistic and look for the kind of real problems in the AI security space rather than some of the non-feasible ones that are being published at the moment. And yeah, the kind of primary talk around bin2ml, the tool that I'm going to kind of introduce you all to, is driven by the part-time PhD that I'm studying, kind of in the evenings and weekends, which is focused on machine learning and AI for particularly reverse engineering, but we're also moving into kind of VR, which is, again, part of my background. So the plan, to give you everyone an idea of where we're kind of going. So I've got a section on the motivation, just to kind of tell you why I'm doing the talk. I've got a section on some background with a good kind of ample amount of memes, so that hopefully should be good. I'm going to go through kind of the problem and take you along the journey of where I kind of started as a PhD student and kind of in the sidelines, and then how I ended up creating bin2ml and why I did that. And then I'm going to go through kind of the reason, like why I've designed bin2ml the way I have, how far we've got so far, and kind of what sort of data you can generate using it, and then go through some of the plans of the future. And it's a bit of a call to action from the audience to try and get involved. And then go through a bit of a summary, and then very heavily plug the workshop that no one signed up to. So please sign up to that. So as a motivation, so why am I doing this talk? So firstly, obviously, is to expose bin2ml to the wider community. So I've spent quite a lot of time on my own with my supervisors and some of my kind of ex-colleagues in various organizations kind of developing it. But not very many people are aware of it, so it's trying to kind of bring that kind of to folks. There's also, I've been in the middle of kind of a very, very specialist machine learning people and very, very specialist kind of VR, reverse engineering, binary analysis people. And I'm kind of quite passionate about kind of bridging the gap between those two and actually getting the two people talking to each other. Particularly, a lot of the reason that a lot of binary analysis people think machine learning is rubbish or isn't as good as it is because it's described incorrectly and it's not kind of realistic and the assumptions are incorrect. And that's where binary analysis people and VR people can actually shape those assumptions to make the machine learning people create solutions that are kind of correct. So as a background, so everyone will have seen over 18 months or so, the large language models, GPTs and everything are just absolutely everywhere. I'm Woody in this situation about 6 months into my PhD, seeing all of my cool research ideas just disappear off of the face of the earth with everyone doing really cool blog posts and whatever. And then we've also probably seen the quantum blockchain metaverse thought leaders that equally pumped out a load of stuff saying, hey, like this is going to change the planet, you're going to lose your job or whatever. But the position, I've done research in this area for quite some time, is very much on automate, not replace. So it's not about getting rid of people, it's about automating the crap stuff that people don't want to do. So in a cyber defense perspective, that might be like filtering logs, for example, or maybe like a binary analysis, finding all of the standard libraries in a function or something straight away rather than having to reverse engineer those. So my position has been, and will always be, that we need to kind of automate the boring stuff and kind of, I kind of say, like, give people power suits to actually kind of achieve their jobs much better, rather than completely replace them. Because how can machine learning, how is it applied to binary analysis? So I'm not going to go into huge detail here, but the big thing is like asking questions like, can you tell me something? So the first one is, what does this function do? So it might be integer or IDA or whatever, and you then put in some sort of representation, whether that be like disassembly or decompiled code or whatever, and say, what does this do? Oh, this is a string manipulation, whatever. You also then got like what do these functions, like what do these instructions do? So it might be you're unfamiliar with an architecture, you've loaded up a binary, you've got to find something in it, and you go, what does this weird instruction I've never heard of do? And then it will obviously tell you. There's also a thing around decompiled code, so there's quite a lot of research which I personally thought was quite snake oily and is actually getting very, very good now, which is then asking, like giving decompiled code and saying, hey, can you change these variable names? The interesting thing, for those who are interested in that area, they're actually applying it to like traditional like static analysis, like data log, for example, and they're combining the two together, and it's mega powerful, and it's, the recent papers are really, really good. And there's also then the kind of more future-looking thing of everything's C pseudocode, which we know is sometimes wrong or whatever. Can we turn it into a Python representation or JavaScript or something else? And that's obviously more of a kind of a fuzzy kind of translation problem, which will probably get it wrong, but it might give you a good enough kind of idea. I just wanted to point out as well, like, rather than me kind of going into great detail, there's a really good talk, and I'm not going to attempt their second names, so if you guys are here, I'm sorry. But Tim and Maritz did a really cool talk. I think it was maybe Recon, I can't remember, titled Unleashing AI, the Future Reverse Engineering of Large Language Models, and they go through a whole kind of half an hour talking about this and have some really good kind of work-through examples. So if you want to check that out, please do. What I've been primarily focused on in the research I've done and kind of my kind of previous research is more kind of asking slightly different questions which don't need generative AI. So it's, does my binary contain a known vulnerability? So given, let's say you've got a piece of firmware, you've unpacked it, you want to check if it's got any known vulnerabilities in the binaries within it, can you check in some way that are known vulnerabilities in here? You've also then got kind of the combo of kind of unknown vulnerabilities, obviously ODAs. That's looking at kind of patterns. So it might be like memory access patterns indicative of some sort of memory corruption vulnerability or whatever. There's also then something that, if anyone's really interested in ML research, this isn't being looked at, is variants of vulnerabilities. So there's loads of kind of qualitative analysis looking at variants of vulnerabilities, and there's not actually any kind of technical kind of research that's kind of looked at how would you actually find a vulnerability and then find 15 other ones of it. So there's an interesting thing about variants of vulnerabilities, and that might be looking at more kind of similar to how you kind of look at two pieces of text and then put them through a model and go, are these close to each other, for example? You might do that in the variant kind of space instead. There's also a thing about like certain functionality. So maybe you're looking for some like cryptography function or C2 or maybe some IPC thing and some firmware thing or whatever. So there's that, which again, you can learn representations of what crypt functions look like and then find n many crypt functions after that. There's also then, which is kind of related to certain functionality, but is a huge, huge problem and something that the approaches are really being able to kind of tackle, which is actually identify third-party stuff. So there's obviously a lot of people think about open source stuff. So maybe you're looking for OpenSSL, for example, or whatever in a statically linked binary. But there's also, and I've kind of previously, in previous roles, actually looked at proprietary libraries that a reverse engineer has actually already reverse engineered, but we know they're in lots of other things. And then using that reverse engineered kind of knowledge and that human's kind of effort to then scale it up across n number of other binaries. And again, that's where I found binary analysis people like the fact that they've done the hard work and then you can then scale it up. So actually, it gives them confidence in its outputs because they've done it themselves. So yeah. So a problem. So now I've kind of given you a bit of background. I'm going to start kind of the beginning. So a long, long time ago, in my office, far, far away, I was reading loads and loads of academic literature. And the image there, I'm not sure if you can see it, is a very happy PhD student being drowned in papers. I wasn't that happy. And I was kind of looking at all these papers, and I was going, oh, these are like really, really cool. And given that I've kind of done some of this research before, I was kind of looking at it, going, oh, this one's not very good, this one's not very good, and kind of created a subset of kind of papers. So I'm just going to go through some examples with you. So, for example, the first one was Palm Tree. So this was one of the first kind of models that used a transformer, so a smaller version of ChatGPT and all the big large language models, to basically learn x86 instructions and then be able to turn a single x86 instruction into a vector of floating point numbers. They then kind of went through a number of different use cases and they basically just collapsed them. They just took the average of the vectors to create a basic block or a function or whatever. But it was one of the first papers that kind of did that. And they did an interesting way of training it where they used kind of linear disassembly, but they also did kind of a data flow kind of approach, which was very noddy, but was the first kind of time it had been done. There was then SAFE, which was slightly before, well, a couple of years before that. This was kind of the OG approach, just one of the seminal kind of papers in the area. And this used the precursor to a transformer and used what's known as an LSTM, a long short-term memory network. But the concept was the same. You chuck the assembly in, you get some floating vector, like floating point vectors out, and then they did some stuff with it afterwards. You then had, it kind of then started moving on slightly, and during the same kind of stage, started actually executing the code. So you put in the disassembly, and then you actually execute it, and you create like a trace of sorts. And then they then put both of those inputs into the model, so it had some idea of learning how to execute the code. It's not that great, though, but the idea was interesting. You then had JTrans that came out again. This was kind of an extension to Palm Tree, and the big difference here is basically they had a task whilst they were training the model that whenever a jump was found, they would mask the jump, and then they would ask the model, where is the target of this jump? And they basically, their representation was just a big string. They just collapsed the function into a big string. And then said, okay, number 3 is a jump. Where does the jump? Oh, it's number 10. And it had to predict that the target of that jump was number 10. Pardon me. And then there was also another one, recent one. This came out of a DARPA program, went completely under the radar, and is by far one of the best approaches. Starts using graph neural networks, which is the focus of my kind of workshop and some of the thing that bin2ml can create. But this one was interesting because it took the control flow graph of a function, but also took the kind of call graph, like the local call graph of it as well, and kind of did it kind of bottom up, which was quite interesting. And the results were really good. The challenge with the approach is they did it on a data set no one cared about, so that's why. So I took some notes and went, don't do it on data set no one cares about. So I was looking at these papers, I was like, oh, this is amazing. I was like, there's loads of research out here. I said, okay, I need to, one of the key things in research is obviously reproducing it. I was like, So Palm Tree uses binary ninja. Trex used its own thing and never released it. Safe used Radar 2. CFG to Vec used Ghidra. And JTrans used IDA. And as someone who's a machine learning practitioner, 80% of your project is data. And I was like, I'm going to have 5 tools. And I said, and I'm doing this part-time, so I don't get the cool Gucci free versions, because I've tried. So if anyone's from Binary Ninja or IDA and wants to hook me up, please do that. And this was my face. For quite some time, I was like, how am I going to approach this? I don't know what I'm going to do here, so this is a mess. And then a ray of sunshine came in the form of a paper from Cisco. And I have to say, again, if any of the individuals on this paper are here, the amount of work that went into this paper must have been insane. It was a crazy paper, very long. The research methods are actually good. They've reasoned everything. It's a really good paper, and they implemented everything themselves. So they released 3 data sets as part of the paper. It compares 10 approaches. At the time, the approaches were pretty good, but obviously because a lot of research isn't dropping codes, they've kind of missed some good ones, so there is some kind of fairly old approaches in there, but it was still amazing. They released all the codes, all the data processing, everything, and they released all the implementations for the models. And then it was IDA again. And I was like, my PhD is focused on cross-architecture function search, and I don't have 15 grand to spend on all the decompilers and disassemblers and whatever. So I was back here again of how am I going to do a machine learning PhD without any data? I said, this is going to be bananas. And then my supervisor was like, hey, why don't you just make one? And I was like, okay. So this is how bin2ml was born. So just to go through, giving you some background and kind of why we're here. So just go through some key design principles to give you an idea of kind of the philosophy behind the tool. So I kind of went with do one thing, and it ended up doing 2. But the idea is that it's basically, it's trying to do the boring thing of just generate the data. And if you want to do anything else after that, you can do your own thing. But the idea is that it extracts standardized data, so it's not kind of in some weird esoteric format that changes every time. The idea is to try and lock in the kind of the data format so it can be kind of shared. There's also then the idea of, I wanted to then post-process that data. So a lot of the time of a machine learning project is you get all this cool Gucci data and you spend ages just doing this monotonous thing of just bug fixing and going through all these weird errors. The idea is that the tool will do that for you, so that the output of the tool is kind of ready to be loaded into whatever, which I'll cover in a minute. Another thing as well is open and accessible. So I didn't want to pay for anything. So the key thing was it must work without you buying anything. So there's some really cool researchers that I've spoken to that, again, also don't have the academic budgets to actually buy a lot of these tools. So I was quite keen to try and make something that, again, leverage kind of free stuff, which I'll go into in a minute. I also wanted it to be completely shareable. So the tools and any data generated by the tool, I didn't want to kind of wrap it up in licensing. I'm quite a there's other tools out there that do that, and it kind of hinders, it kind of makes the decision of will I use this thing quite difficult, particularly for kind of folks in my position that work for industry and academia. It's quite difficult. So I want it to be shareable and just work. There was also then this idea about speed and scale. So I wanted it to kind of fulfill two roles, which was fairly difficult. But I wanted the idea of, I wanted to be able to run it on my laptop and process 10 binaries, and then throw it on my university's HPC and process 1 million. And I wanted a tool that could feasibly kind of work in that way. So that was, again, another kind of design thing, which is kind of what a lot of the processing in it is threaded, for example. So it can kind of scale up to really big nodes. There was also then, this is a bit, I realized I got very confused at this slide when I was looking at it yesterday, so hopefully I can explain it okay. So I wanted it to be cross-architecture and cross-platform. So what it means in two different cases. So the first case is I have a MacBook, a Linux HPC, and a Windows computer, and I wanted to work on all of them because I wanted to process all different types of binaries. I didn't want to have to worry. So that was one thing. But equally, I actually wanted it to be able to process any architecture and any platform. So one of the big things with a lot of the research, a lot of it's Linux-focused, or you might get a random Mac OS paper or whatever, but there's nothing that's kind of looked at kind of cross-platform and cross-architecture, and that's kind of an area that I'm going to move into with the research. So I kind of wanted it to be kind of really like mega flexible. One thing as well, which I'll come back to later, is I wanted to extract once and use many. So extracting data, particularly with like reverse engineering tools, so for folks that have like processed big binaries in Ghidra or IDA, you're spending a long time letting that kind of run through and go through all this analysis and stuff. So I wanted to be able to basically extract that data and run that processing once, and then pre-process it from then as many times as possible. And again, this kind of goes back to sharing. So if, let's say, someone's got a load of compute and they can process everything, they can do that, and then they can then share it with as many other people, and they kind of that kind of, I guess, CO2's been spent, if you know what I mean. You can focus on generating the data. And I also wanted to, going back to the kind of 80% problem and post-processing stuff, I wanted to reduce the post-processing stuff as much as possible. So coming from kind of gov research, you always have a stakeholder, I've got some really Gucci data, and you spend months trying to just unpick this pile of rubbish. I wanted to eliminate that and basically just have it so you could just, as soon as you know your data, you can load it straight up and start experimenting with the models, which I think, particularly in this space, is where we've got a long way to go. There's like the models that are being used are very, very, very noddy when you look at some of the other literature, like in computer vision, for example, we're miles behind. So, the story so far. So, it's leveraging the open source SRE tool Radar 2. I know Radar 2 slightly is sometimes controversial, depending who you speak to. But the primary reason for me doing this was it's got R2 pipe, which was a really cool kind of way of interfacing with it. You basically just feed it the actual command you do on a command line in the command line tool, and it will just spit it back to you. There's also then the as-JSON commands, which again give me my kind of standardized inputs. There's loads of checks around that, so if it changes, it will break and say, this is broken, you have got different data, so that we can't really, if they do change it, it will know. There's also a really cool range of plugins in there. So one of the key ones was R2 Ghidra, so that goes straight into Slay. It's a C++ kind of extension, which again is quite quick and performant. And I also wanted it to be, again, because I was doing it on Windows, Mac, whatever, I didn't want a load of dependencies. I didn't want to have to install all this stuff. So I just wanted to be able to install Radar 2 and just get going. And there was also an idea as well, is obviously Radar 2, and particularly Pancake, the kind of primary contributor and kind of maintainer of it, they're quite receptive to kind of problems, and I actually quite like that I could say, hey, this isn't working or whatever, could you fix that? And there have been cases where I've had conversations and I've raised issues on Radar 2 going, this weird binary isn't working or whatever, and stuff like that. And obviously when they make the change, we get the change straight away. So for those who have kind of come from a data engineering background, the ETL is kind of what data engineers do, which is extract, transform, and load. So I've changed it slightly, so the verbs in bin2ml, T has been replaced with G, which is generate. But the idea is that you extract, you put a binary in, you extract with Radar 2, which then kind of bin2ml kind of wraps the input, the output, and the saving of that. You then load it back up to bin2ml completely independently, and then generate whatever data you want, whether that's a graph or whatever, which I'll go through in a minute. And then you can then load that into kind of frameworks like Hugging Face, PyTorch Geometric, etc. And the idea is that all the outputs here are JSON, so you can really, you just load it. Like it's quite trivial to put that into any framework you wanted to put it into. So I've got quite a long bit on here around all the different things it can generate. And if people can start nodding if this is getting boring, it'd be useful. I'd appreciate the cue, but I'll start from the top. So what can we generate? So the first one is control flow graphs. For those who aren't familiar with a control flow graph, it's typically function level, and basic blocks are kind of a contiguous set of instructions, and then kind of the edges are kind of jumps or fall-throughs or whatever. And this is actually big enough, so you can read that. That's really good. So you can see on the, I'm not going to attempt, the first one, where we've gone extract test binary, we want to output it to where it is, and then we just want to have the CFG data type, which is the control flow graph data type. And then we've got on the next stage, which we just want to generate graphs from the JSON output, and we want the disassembly. So you can see, if that's big enough, I think it's big enough, you can see that's some x86 instructions, which are the basic blocks. The output, the graph output, is a network X JSON object, so you can just load it up in Python straight away and save that to any other JSON type, any other graph type that network X supports. And it's all kind of been validated and actually loads well, and all the data will be in there and everything, so yeah. Alternatively, all you have to do is just change the F flag to Gemini, and you'll get the Gemini paper, which is a kind of a seminal graph neural network paper in kind of function search. You'll actually get the Gemini features as the nodes rather than the instructions. And I've also implemented Discover-RE, which again was a new one, DGS and TICNIB, which again, you just change the flag and the features in the nodes will change to the features matching those in the paper. Alternatively, I think this might be the one that the mermaid graph went a bit skewy for those who are eagle-eyed, but hey. But let's say you want to actually on ISL, which is the kind of IL, IR within Radar 2. Again, you just change the ISL flag, and it will generate you a control flow graph with ISL instructions instead. And even, again, if you want pseudocode, you change it to pseudocode, and you get pseudocode. And again, just to highlight, if it wasn't clear, we haven't changed the extract flag. That's been done once to generate all of those different types of data. So that the expense has already been spent. And you'll also notice on the generate thing, that -n is a number of kind of workers. So again, if you had like a 500 core machine, you could feasibly set that to 500, and it would process it with 500. So yes, so I've kind of got it to about, there's a HPC node at uni that's got about 2,000 cores on it, and it works. The only thing that slows it down is then the hard drive. But hey. So this is kind of good for learning about graph neural networks. See you guys at the workshop, everyone. And then the task-wise, you've got kind of binary function search, which is what my kind of PhD is primarily focused on. You've got end-day detection. You've got function level functionality prediction. And there's kind of lots of different tasks you can kind of do this sort of stuff. And also, if you want to replicate the research, we can obviously replicate Gemini, because we've got the Gemini nodes. And there's also a paper, a really good paper, called Graph Matching Networks, which again, you can replicate by using the Gemini features straight away. So you've also then got cool graphs. So again, highlight the only thing we've changed on the first box is we've changed the mode to CG. And then we've then got generate graphs, blah, 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 and we put the data type as global CG. And you will get this kind of the global control flow graph, so all of the functions and all of the edges and whatever. Caveat, obviously, Radar 2 might not recover that correctly. So, but hey, like whatever it has recovered, it will give you. And then we've got an alternative, which is called in the literature, it's called n-hop call graphs, and I've implemented a part of that, where it's one hop, and the idea is you take the callees, the callers of a function and the callees of a function, and then create kind of a localized kind of graph. And then, for example, if you did main, in this case, you would get everything in the red, and then if you did foobar, you would get everything in the blue. And again, this one's interesting. So those who are interested in graph theory, because sometimes control flow graphs are quite small, so it's not really useful. But if you're interested in like kind of, if you use like the Linux kernel or something, which Radar 2 might actually break with, so don't do that. But the idea is that you can learn graph theory techniques. So if you're interested in things like betweenness or centrality or page rank, stuff like that, and you want to use like a data type that you're familiar with in a binary analysis case, it's a really good way to start. And again, it's all kind of JSON NetworkX objects, so you can load it into NetworkX and start kind of hacking about in a Jupyter notebook or something. So in terms of kind of tasks, so you can do binary level searching here. So this, I did some research a while ago, looking at using these for finding kind of malware variants and stuff like that. So again, you could do that. You've also got the idea, particularly with the kind of n-hop ones, you can do kind of inter-procedural function search, which is interesting, and it kind of is linked to the fragment idea. So, for example, maybe a particular malware has a really obvious obfuscation pattern that they always use. You might be able to find it using that. And in terms of replicating research, there's the PSS paper, which is from a group of French folks, which is really interesting. It uses spectra, graph spectra, to kind of do binary level stuff. And it's really simple and it's actually really powerful. But it has a slight issue with if the graph's very small, you can never find the first eigenvector that they're looking for, and it doesn't work, but we'll rush over that. And then KYN, which is Know Your Neighborhood, is a recent paper I've just dropped, which uses the n-hop kind of call graphs and beats most, if not all, papers across a number of benchmarks, and is so noddy, it's kind of embarrassing writing the paper, but it works and it's good. So moving on quickly to disassembly and ISL. So let's say, for example, again, CFG data type, we haven't changed the extract, so this is the same JSON file. But let's say we want disassembly and we just want single, so we want a linear walk across a function and we just want it in a big text file. So again, we can do that. Again, we just change it to ISL. We get exactly the same for ISL. But let's say we want to change it slightly and we actually want to have a random walk. So you get the control flow graph, you explode each of the nodes, so every single line is its own node. And then you just random walk it. So you just kind of follow the graph, and you just kind of randomly take edges or whatever. And you want to pair it up. So this is, for example, if we go back to the palm tree approach, this is how they train palm tree. So this is the input data to palm tree. So again, you can, as you'll see in a minute, you can train palm tree. And again, if you want ISL, you just say, I want some ISL, and it will give you the ISL. Alternatively, you've also got the idea of the function strings. So if you go back to when I introduced JTrans, this is the data type for them. You'd have to do the jump instructions without the knowledge in JSON, which that's a bad time, but maybe someone wants to add that to the tool. And equally, if you want to do ISL, you just say ISL, and you get a function string that's ISL. So this one, again, is interesting. So this is, again, this is a natural language approach, so rather than all the graph-based stuff we had before. So this is kind of NLP stuff. So the first representation of kind of single rows is really good for training tokenizers. So a tokenizer is what converts kind of input into kind of scalar numbers, which then are used to go into kind of the pre-processing step before you put the input into a language model. Again, you've got binary function search, etc. But then this allows you to also replicate research such as SAFE, Palm Tree, and then another one of the papers that I did, which was Phaser, which uses ISL function strings instead, and it's on par with a lot of stuff, aka not great. So for those who want to use IL, really cool idea, pretty rubbish. So moving quickly on, so we've got decomp and P-code. So I had again, I don't know if they're in here, I don't know their actual name, but someone raised an issue and said, hey, can you add like R2 Ghidra, and I want to do some decompilation stuff. I said, hey, let's do that. So kind of wrapped the decompilation stuff and kind of done some formatting and whatever. So you basically just say extract test bin, boom, and you'll get the decomp out. Obviously, if you did this in Ghidra, you could do passes to like fix things. This has no functionality to do that, so you're basically getting kind of the raw. It's not great, honestly, and there's probably a lot of kind of things that can be done to kind of clean it up. So one of the things I'm planning to do is get rid of all the weird comments in it, or they kind of say, can't recover this, can't recover that, or whatever, hopefully to get rid of that. We've also got P-code in a similar way of the language model, so you'll see we've changed the mode to P-code basic block, so that basically gives you a control flow graph-esque JSON object that has the P-code for each basic block. Very similar. You say, hey, I just want singles, and it will give you kind of singles in a text file. Again, you can do that with control flow graphs as well. So you can go, hey, I want control flow graphs out of this, and whatever. I think one of the things that this is good for, and I found quite useful, is you can quite rapidly prototype P-code stuff that doesn't need Ghidra. So there's things like, I'm not sure if people have come across CWE checker, for example, from, I think, Fraunhofer. They've kind of interfaced Ghidra to get the P-code, and then they put it into an IR, and they can do a number of analysis, kind of static analysis on it. I found the code quite difficult to kind of unwrap, so I ended up processing things in this way and their way and going, what are they doing, how are they changing it and stuff. But equally, really cool for training tokenizers. So I think P-code-based models, again, haven't been explored and are going to be, particularly for those that are working for particular partners, are probably going to be pretty good. And obviously, it can, again, do all the kind of usual kind of things. There's a recent paper called Hermes Sim, which was at Usenix. It's going to be published soon, or like presented soon, sorry. They do a really cool approach where they turn they use P-code to create a graph, which is the memory input and output operations of a function. And their results are really, really good. But the challenge is, for those who are paranoid like me, they give you a compiled jar file and say, download this and run it. And I'm like, no. So that's a shame. So there is a plan. I'm kind of planning to see if I can try and recreate what they did. Maybe decompiling this jar and checking it first and not just randomly running it. So there's a bit of a B list here of things that the tool can also do, but again, I didn't want to kind of bore everyone to death with lots of screenshots. So there's like function and binary metadata. So this is really good for tree-based approaches. So things, if you wanted to do like XGBoost or something like that. So it can pull out things like number of local variables and how many instructions and how many basic blocks and complexity and all that sort of stuff. There's also the full range of NLP stuff in the P-code stuff, so you can generate pairs, strings, whatever as well. There's also local xrefs, which the extraction functionality has been done for, but I'm currently doing the graph functionality, so the idea is to be able to make a local xref graph as well, which again another paper tried to do. There's also, which I think is really important, and those that who maybe are new to machine learning research but are interested in getting interested, like deduplication and cleaning the data is mega important, and the amount of research out there that just forgets this and reports amazing results is quite profound. So the tool includes a method of deduplicating like millions of graphs, and it kind of does it iteratively. So I think for the KYN paper, I deduplicated like 7-8 million graphs to try and like get rid of all the duplicates. And including the duplicates is like a 15% performance increase. So it's like they're very much publishing snake oil if they haven't if they haven't done the kind of dedupe step. And there's also, as you may have noticed, a lot of the hex values in the examples are actually masked out and have got different tokens. So for memory addresses, it's mem. For function calls, it's function, jumps, whatever. And the idea there as well is, well, if you're doing kind of natural language processing, you obviously need a vocabulary of all the possible things you were looking at, and that kind of reduces it. So to the future. So we're on the home straight, guys. I haven't pressed the timer, so I haven't got a clue how long I've got. But anyway, so the next thing is looking at multiple modalities. So a modality is a type of input. So for example, a model that can take the graph representation and the instruction representation together and then combine them together is kind of an idea that I've got. And there's also an idea of merging modalities, so maybe having a data flow graph and a CFG together, for example. This is kind of a bit of a call to folks that are kind of Ghidra, IDA, etc., whatever tool of choice wizards. There's nothing stopping people from writing different backends that can do the extract stage of this and still load the extracted data into bin2ml to then generate the kind of outputs. So yeah, it'd be really, really cool if anyone's kind of a wizard and wants to do that. That'd be great. There's also, I've got quite a few plans for kind of more graph features. And what I mean, there's some research that do like, if you symbolically execute a number of, let's say a number of basic blocks, you use the actual symbolic representation as the input into the model, or you simplify it in some way. There's some interesting stuff there. And there's also a load of things around, like, can you use, like, how do you best represent a basic block? Do you do data flow within a basic block? Can you simplify it? Can you, yeah, there's loads of kind of options there, which I'm hoping to explore. There's also some interesting stuff with more kind of advanced static analysis stuff. So one of the areas I'm really interested in is e-graphs, if anyone's come across an e-graph. And basically what e-graphs allow you to do is they're basically like an optimization technique, and you create rules and you can kind of collapse and optimize different things. And obviously because P code particularly is a representation which you can kind of put into kind of single static assignment, you can use e-graphs on them, and there's potential to actually, let's say you've got a really complicated thing, you can kind of smush it down. There's also another thing, this is more of a general thing. I'm hoping that now that there's a tool available and hopefully everyone can tell all their friends about it, I'm hoping more people will do some ML research in this space. I think the barrier to entry, it seems quite intimidating, but it's not. So please come to the workshop and I can demonstrate kind of some of the models, and you'll be getting really good performance quite quickly. But I think the key thing, as I said in the beginning, is a lot of binary analysis, people think it's a bit snake oily, and I think it is at the moment. And the reason for that is that people like yourselves aren't inputting into the process and aren't going, that assumption doesn't work, like that representation is wrong, like this could be fixed, et cetera, et cetera. So I worked, I won't name him because I think you'll probably know him, but I worked with quite a experienced reverse engineer for quite some time at a previous role, and the solution we managed to create together was really, really good. And it was solely down to getting my assumptions correct and him going, no, you need to change this, you need to change that. So it's really a call to action to everyone to have a hack around and yeah, see what happens. So just as a TLDR for those either who skip right to the end of this when it gets published or the people that fell asleep. So an open source tool to convert software binaries obviously into ML. Get involved and get hacking around, please. And obviously, if you're interested in kind of getting a bit more hands-on and chatting or whatever, please come to the workshop, which I think is in 15 minutes straight after this. Thank you.
So yes, we have a couple of minutes for questions. Thank you, Josh. And just to repeat what Josh said, he is running a workshop going into more detail on this right after this, right over there in 15 minutes. So wander on in.
Hello. Do you have any plans to also explore DFGs or like diffuse chains?
Sorry, I can't hear you.
Do you have plans to export DFGs or like diffuse chains in your tool?
Yeah, so the local XREF feature is kind of the beginning of that. But the idea, if I'm honest, I'm kind of reading a lot about the kind of abstract interpretation and data flow analysis and all that stuff at the moment. So I'm kind of learning it, honestly. The plan would be diffuse chains is quite an interesting concept, and it's definitely something I'd like to add. But I'm not going to kind of claim at the moment to have the knowledge to add it yet. But now that the P code can be outputted and it's in kind of quite a structured format, I'm hoping that will kind of allow maybe some kind of post-processing to then actually start generating that sort of stuff.
He said, because it makes it easier to.
Yeah, so basically, if you have the P codes, basically the input and output relationship would help you to create.
Yeah, it's very clear, isn't it? Yeah, hopefully.
Any more questions? All right. Thank you very much, Josh, and I hope everyone goes over to your workshop.
Thank you.